And now, one more presentation for your enjoyment. We have Rob Robinette, Alpha India 6, Victor November, and he will be doing a live demonstration, which is, I think, is always dangerous. But a live demonstration of Kiwi SDRs on the web.
Okay.
So, thank you, Rob.
Thank you. Well, I'm honored to be here. Thank you for inviting me. And I bring to this, my background is primarily computer systems. I lead a company that builds video compression, professional hardware. So I'm relatively unfamiliar with all the issues associated with RF. I was a ham for my youth and then returned to it only a couple of years ago. But I have become very interested in it, and specifically I've been working a lot with Kiwi out in California. So I thought I'd give some insight into the Kiwi itself. I think I can skip this over. I mean, this is a Kiwi. If you haven't seen one, it comes. It's sold bare bones. You can buy the card, but really, for very important reasons, you want to put it into a metal case. The A to D converter's number of bits is one thing, but the effective resolution of the whole system depends upon having a very, very low environment, self RFI environment. And it's extraordinary. With the case on it, really, it sits there at the noise figure of the Kiwi itself. It's remarkably insensitive to differential power supply noise. You don't see a 200 millivolt, 54 kilohertz signal on the output. That's amazing. So, my understanding is it's an LTC 2248. They advertise it as a 14-bit A to D. So my understanding is it's a 14-bit system, and it clocks at 66 megahertz. Yeah. Well, I think that the one that actually is out there right now is 14 bits. It's in front of it is a 20 dB of, I don't know, 1 nanovolt per root hertz op amp with a low-pass filter. It's a complete RF system. So in contrast to the Red Pitaya, which is really, a very general purpose device, this is purpose-built and optimized for high-frequency RF reception. And I was amazing. I did not really appreciate the importance of the oscillator, and I will show you the performance of the internal oscillator live, hopefully in a few minutes. But the external oscillator is really essential, I think, for Doppler shift measurements, and I think that it has a significant effect on, I realized, on signal noise ratio at higher frequencies. So we have one Kiwi modified that has a Bodner, and I'll try to show that to you in a few minutes. There are provisions for external clock input. There's a pad on the printed circuit board, and there's a software support on the web page, administration web page, where you can set that as your clock source. Standard SDR display, waterfall, spectrum analysis. Its noise floor is, in 3 kilohertz down about 124, minus 124 dBm. So this is a spectrum from KPH in California. It has a number of built-in extensions. There's a built-in whisper decoder. So you can go to any available Kiwi, select the whisper extensions. It will go and start decoding. You select a band, it'll go start decoding. Show you a waterfall that up in the upper corner. I don't know if let's see. Well, yeah. This is the standard waterfall. That's a 200 hertz right there, bandwidth. This is a zoom in, this waterfall, and you see labeled the signals that were detected in the last 2-minute window, and you can see a list down here. This is I think the best demonstration for the neophyte of how Whisper works, and it's a wonderful viewing environment. However, it's a challenge. The Kiwi is challenged by a rather low CPU horsepower. And this decoder is a port from a rather old WSPR D decoder. So the performance of the actual internal auto decoder is relatively poor, especially if you have many signals, as I do at KPH in California. I'll decode 30 signals in 1 2-minute window. It can't decode more than 10 of them. It runs out of time. So I've spent the last year primarily writing an external package that runs on a Pi and talks to, it's an external extension to the Kiwi, and I think one of its greatest strengths is its extensibility. This is an example of an internal extension. If we go, there's another internal extension, which you'll see live in a few minutes, which is the IQ display. So here we are, we're tuned to, I think this is, this is WWV at 25 megahertz received at my friend Glenn, N6GN, lives in Fort Collins there, about 10 miles from WWV. So this is an IQ display. Again, this is a built-in extension. You can just go over here to this pull-down menu and select it, and you'll get this display. There's a whole series of extensions, built-in and user-contributed extensions to the Kiwi that are available, many of which aren't of particular interest. Fax decoders, a CW decoder. There's strange, doesn't work very well, but anyway, it's an interesting example. Again, with the Bogner driving the Kiwi, you get much, you get the Bogner's frequency accuracy and phase noise. And this is like, I don't know, several minutes worth of IQ display. You can see that at 25 megahertz, the Bogner and the Kiwi hardly vary from the frequency of the WWV. This is line of sight. There are external extensions. These use capabilities of the Kiwi, but a group of the Kiwis. And one of the startling examples of the way the Kiwi and a group of Kiwis can be utilized is this TDOA, time delay of arrival extension. And this uses, you select, in this case I selected 3 sites, actually kind of far away sites from WWV. You select them down here, you hit a button, the submit button, and a cloud server goes and grabs 30-second recordings, WAV files from these 3 Kiwis of this signal that you've tuned to, and processes it on the cloud server, and then displays a heat map showing you the location based upon the location. Now, this in and of itself, I don't think is, a great area of interest for this group, but I think it demonstrates the power and extensibility of the Kiwi and of an existing in-service network of 400 Kiwis around the world that you can log into, and all of which have this capability and can be used for studies. This site is, for example, of course, these Kiwis vary in their quality of their GPS connectivity, the quality of their antennas. Who knows, what they are. One fellow has come up with a technique that he's going out and created this map which shows, tries to show the quality, SNR quality, of various Kiwi sites publicly available. So if you want to find a site in a region that you think has a pretty good signal-noise ratio, good at receiving, you click on here and you'll find that's my little farm on Maui, which is one of the better received sites out there. But you can find a group of Kiwis that are accessible to you, and you can record for them. There is I use a extension to the Kiwi Recorder. It's a Python utility that runs on, in my case, I run it on a Raspberry Pi, and it records WAV files, and you can, which I then process on the Pi. That's how I can run 8 channels, Kiwi and 8 channel, and do 8 channels on one Kiwi simultaneously. and use the release version of the WhisperD decoder. So anyway, these sites are available. There's, of course, this fellow actually is logging all of the signal-noise ratio data from all these sites. He goes in every 10 minutes and grabs, I don't know, 10 seconds of data from each of those 400 sites and puts it up. So there's noise plot data over, this is a week's worth of time at different frequencies bands. So again, I don't know that this is this application is maybe not immediately relevant to us, but it's an example of the power of and the openness of the Kiwi environment. So there's, of course, the SDR.hu. You can find Kiwis anywhere. You know, this is the whole list of everybody who's made themselves publicly available. In my case, I put together at KPH out in California, at Point Reyes National Seashore, which is about 30 miles north of San Francisco. This is a historic radio site established, well, the station was at one point owned by Marconi, I think, but Dr. Beveridge of Beveridge Antenna selected this as a receive site for the maritime radio service, and they established this, built this station out there in 1928. It went out of commercial service in '99 and has been taken over. It's part of the National Seashore National Park. And a volunteer group is then operating it as a demonstration living history museum, where they, every Saturday afternoon, and if any of you come to the San Francisco area, please come out there on Saturdays, they'll show you how radio operators used to communicate with ships during the 30s, 40s, and 50s and 60s. There's only about 4 or 5 other stations operating similar kind of right now, but there's a whole host of antique radios, including this working 1920 ear horn type antenna that's sitting in a back room. I've added, in the last year, added to it a small rack here filled with Kiwis attached to their antenna systems. And this is the bank of, well, you can see there's actually eight Kiwis now. There was 10 at this time, and I take the incoming signals, low frequency. This is a Marconi T antenna for the low frequencies. It has to have a bandpass filter. It's a 14-bit converter. It'll get overloaded. I mean, you could almost fry an egg on the signal coming off of that T. The others are coming from a distribution amp off of a TCI 530, which is a commercial antenna system. It doesn't require filtering in front of it. So, and then I take the GPS, and I have a passive GPS distributor. So all of these guys they're tracking 10 or 12 satellites simultaneously. So as a result, the Kiwis, well, there'll be more information there, on my presentation, where you can go to see go to them. Included, you can open kphsdr.com, just open it, and it'll take you to one of those Kiwis you just saw. So what I was going to do was try to show you a live demonstration of how the Kiwi works. My mouse isn't working, so maybe this one will work. So this is up here. Here's WWV, Fort Collins. Here's the remote site. I guess I'm not exactly right, but this is on a mountaintop operated by my friend Glenn Elmore, N6GN. So he lives down here and has a Kiwi down here. And he on a mountaintop, which is line of sight. Literally, he can see the antennas here. This is a 20-kilometer line of sight. He's at about 8,000 feet here, and this is 5,000 down here. So he has line of sight ground wave to all of the WWV signals up there. And this unit, sitting in an unheated room in a cabin up on the rooftop, is driven by a Bogner clock. This one down here in his house, well, temperature controlled, does not. It only has the internal GPS. So if I can hide this, and let me bring up, here's a live, I'm sorry? Yeah, the audio, I could turn it on, but I thought they should be off. I didn't want them on. I don't think you want to hear WWV, so but you can see here on the left, well here, let me clear the IQ display. This is the IQ display, drew a circle in 45 minutes. So that's 1 hertz of error, I think roughly 1 hertz of error over a 45-minute period. So I'm going to clear that. You're going to see right here is the IQ display, and it will very, very gradually move. This is, on the right, this is the Kiwi at his house, and this is the GPS referenced, okay? So that's 1 hertz of error of drift in 4 or 5 seconds. Still very good at 25 megahertz, but nothing like this. So you can see it wanders back and forth. Again, there's more noise here because his signal noise, this is a minus 82 dBm. These are set up for 10 hertz bandwidth. So this is 10 hertz wide. And there's, should be, this is minus 54, so it's, 30 dB stronger. So you can access these from your phones right now. They're available on to you on the internet. And so this is how, the user interface. I don't have a good way to show you how to access it remotely, but there's a Kiwi Recorder Python library. It provides for that. One of the interfaces is to record IQ samples with a microsecond accurate timestamp prepended to them. So you can gather samples simultaneously with timestamps from GPS-trained Kiwis and process them whichever way you want. That's not my area of expertise, but I have, I do have a whole group of these systems working. It's extremely reliable. The recordings are absolutely, they run 24/7, 365. The whole library is completely debugged. There were bugs, but I helped John debug it. It's very low, the Kiwi itself is extremely low noise. Our biggest area of research now that we have all of this I have all my software working is to improve the quality of the receive environment. And we're working on a very high impedance, short active antennas that will show great promise in being able to cancel out local QRM sources. So the number of bits of your ADC does you no good if you're picking up the local, Walmart. And we've been able to get and this is sitting at a local receive location. This is a home location with an active antenna. And if we look at this, you can look at it yourself. In a 3 kilohertz bandwidth, it'll be down about minus 118. It's maybe 4 or 5, 6 dBs above a super quiet location. There's an ITU specification that tells you what to expect in terms of rural or urban locations in terms of the background noise level. And for many applications in signal processing, that's what limits you, is the noise generated by local sources. And how do you actually make use of all those 14 bits? Anyway, I should stop. I'll be demonstrating this tomorrow at a site, but I think what I encourage you to do is you can go to sdr.hu, go to look at Kiwis, explore the feature of the Kiwi, and know that you can gain access to this and make it part of a larger system, a cloud-based data gathering system. Okay? Yeah.
I stand corrected. You are right. It's 14 bits. I got wrong information somewhere.
We all make mistakes.
I will update the presentation that will be uploaded on the site.
Yeah. Yes. Yes. It's not a DO. Yes, not a DO. It's not a disciplined oscillator. It's a reference. What he does is he takes the pulse. He has a counter running on the pulse coming out of the GPS. He compares it against the count coming off the local oscillator and uses that to change some registers in the for compensating for it. So he's compensating for the error between the internal oscillator and the GPS signal. So absolutely. I mean, especially when I learned from is it John's presentation? The importance of phase noise. I'm now going to drive all my Bogners off of. All my Kiwis off of Bogners. It's clearly there's 3 or 4 6 dB of signal noise improvement available, I suspect, over that internal oscillator, and that made this whole trip worthwhile to me. I didn't appreciate it. So I have to go out and buy a distribution amp, and I'm going to drill holes in those 8 Kiwis and modify them all, and it'll be a lot of trouble. You create a lot of work. But I think my experience is that in terms of whisper detection, if you get 2 or 3 or 4 dB, 2 dB is enough to raise your spot count, your detected signals, by 30% or more. There's a tremendous, there's an asymptotic kind of improvement as you improve your signal noise ratio. So that happens with improving your antennas or clearly improving the clock. I didn't appreciate that. Yes, someone else.
Yeah, I just wanted to mention that there's another historical, very low noise site, KFS, that is south of Half Moon Bay.
Yes, there
right
is.
Off of Highway 1. That's on WebSDR as well.
Yes. Yeah, I've tried to contact those guys, and I was trying to, now my experience, they have a TCI 530. It's a pretty good location, on the bluff. I did one test for an hour where I did whisper decoding off of the KFS at 20 meters and compared it against the decoding I did on from KPH, and I was 3 or 4 dB better at KPH. So I think it's still a better site. Thank you all. I've taken more than my time.
All right. Thank you very much.
Okay. Thank you.